My reference for the hyperbolic graph construction and many of the claims and lemmas about it is the paper on the screen by Bjorn and Shammeglingem. It's a beautifully written paper. The first 5 chapters can be read by any first-year graduate student, basically. And my conventions and notation are mimicking that, except they use Z for the space they begin with. I use X, and they use X for the graph. I use G for the graph. When I deviate from their conventions, I will point that out. I have 3 pictures which basically capture everything. If you start with just a singleton x0, then all your ANs are x0, but still the graph is infinite because the levels keep going up. And then we saw that the hyperbolic graph here will be just a copy, isometric copy of 0 to infinity. So in metric world, this is just equal. And then with the finitely many points, I went into some detail of explaining why there will be some level after which there will be no horizontal edges, so it will be all vertical down. For S1, I like to draw this hyperbolic filling from inside. You can also view this as if you're watching this hyperbolic graph from on top, from the sky, a bird's eye view. You're standing right above W0, which is the root vertex always, and when you view it from up, you see a flat picture like this, which explains the word filling. If you are familiar with the hyperbolic geometry and the Poincare disk model, there is a metric inside the Euclidean ball, which is the hyperbolic metric, and its Gromov boundary is S1. So in that sense, the word filling finds some justification, and the hyperbolic part in the wording will also be justified in a second. So let's see what structure we have so far on G. It's initially just a combinatorial graph, a bunch of points. By the way, these levels in general can be infinite, and we will see when they are finite. Each level could have infinite many vertices. So G with path metric is a metric space, and the next claim is that G is geodesic. Maybe the last part about being geodesic needs some argumentation. It's not completely trivial because there could be infinite number of vertices at each level case. So exercise prove last part. Theorem, again, I refer to Bjorn Shammeglingem paper for a proof. With any choice of alpha bigger than 1, tau bigger than 1, just to emphasize, the graph G with path distance is Gromov hyperbolic. So we had explained why it's called filling, and now we know why it's called hyperbolic filling, because it is a hyperbolic space. I'm not going to go into details of what Gromov spaces are, therefore I won't also give a proof of this theorem either, because the way we will construct or recover rather X as the boundary of the graph, we'll use a different technology, which at the end of the day is equivalent to this Gromov hyperbolic business. When you have a hyperbolic space, you can talk about what is called its Gromov boundary or visual boundary, and it comes with a metric. So therefore, graph G with this distance has some boundary, which is a metric space, and the claim is that that boundary, Gromov boundary of G, becomes by Lipschitz sometimes quasi-symmetric to the original space you had started with. So this is one way of making sense of the claim that boundary of your graph is the original space. But we won't take this path. Again, we will not take this path. We will do a more explicit and straightforward way of making sense of what boundary of G means. Meanwhile, as I had explained again earlier, you cannot easily talk about boundary of these spaces without something. And the reasoning, if you recall, was that this space as a metric space is complete, so there is no boundary. All of these ends, you cannot just say something is waiting here for these. Because we can draw this picture doesn't mean the boundary is there. Mathematically, there is nothing missing in this space, because if you take Cauchy sequences, their limit is within the space. And finally, in this picture, because I have drawn it this way, the most convenient and beautiful to me, doesn't mean S1 is really the boundary of this graph in the interior. You have to make sense of it. Again, this graph is complete as a metric space. It's only artifact of my drawing in a bounded part, an infinite graph, that it looks like these tails, these ends, are converging to something, which is S1. That is not true. My picture is lying again, because all of these edges have length 1 according to my construction, no matter how I draw them, which is very deceiving. All these edges, no matter how small I draw them, they should be viewed as isometric copies of 0, 1. So every ray you take, let's say this way, will have infinite length. It's a copy of basically again 0 and infinity, and there is no end to it waiting here. There isn't something here, just by this naive approach again. But if you go into the notion of Gromov boundary, you recover S1. We won't take that path. Instead, we will change the metric on G from something that looks so large to something more controllable. And once we do that, that space will have a boundary, and then we will prove that that boundary is our original metric space.